Okay, hello, this is working, yeah? Okay, hello everyone, my name is Hugo Gonzalez. I work at CERN IT Storage Group. My talk today is about how to break the monolith for sync and share and an example use case using my baby, yeah. So my talk is going to be scheduled like that. I will start with a little introduction to microservices, what is the current monolith, what are the requirements to have a microservice-oriented architecture, what is ClawIO, and what is the comparison between the monolith and the microservice-oriented architecture, and finally some preliminary conclusions. So, microservices is a new architecture that allows to structure the application in very little components that are loosely coupled, so you can really start collaborating between these little services using lightweight network protocols. It has been adopted by very big companies and currently has a lot of hype, and few companies to mention are these ones. The objective is that nowadays many open source and sync share vendors have a monolithic platforms run as monolithic. So I wonder myself, is it feasible to move to a microservice-oriented architecture? What are the benefits? What are the costs? I decided to build something in order just to test if this was feasible or not. So this is the current monolithic approach for many sync and share platforms of today. You have different logical components for handling like data, synchronization, sharing, the web user interface, authentication, authorization, and a lot of more logical components. And usually this monolith, usually I cannot see here the real slides, connects to different external services like a storage system, a database, Active Directory for authentication, and third-party services for integrations. If you want to scale the monolith, okay, the PDF is completely broken. You have a load balancer on the top, and then you just copy and paste the monolith for increasing the, like say, the reliability of the service and trying to scale. And at the end, what you have is like you have a mess in the bottom. You have a lot of connections to the different storage services. What are the pros and cons of this monolithic architecture? Is that benefit is that you don't have network penalty because the interaction between the logical components is made in memory by inter-process communication, and you have simpler deployments. Everything is self-contained, so just copy and paste, and then you have another box with the same state as the previous one. What are the problems with this monolithic architecture? You have cross-boundary overhead, so if you have your monolithic server running different applications, one application that is non-critical can impact the performance of the critical path. For example, you have thumbnail generation. This maybe impacts the, let's say, the file upload or download of a real user. Also, it increases the complexity. Having large code base, it increases the complexity for managing the code. So usually, it tends to be like less quality the code over a long time. You have also different logical applications in the monolith, so you have different resource requirements. One part of your application can need a lot of memory, and another maybe need a lot of I/O or a number of CPUs. And at the end, you have the monolith. You end up buying the expensive machine that has everything. Also, adhering to agile principle is difficult. You have a large code base, so the time when I commit something to the time I get the feedback that it has passed all the integration tests and is deployed in a testing environment, it can really last some hours since I get the feedback. Also, it really requires a long commitment to a technology stack. If you have a monolith, rewriting some parts of the code can be really difficult and can cost both money and human resources. So you're really trapped to a technology stack. So as an anecdote, in August 2008, Netflix experienced a major database corruption for 3 days, and they realized since that day that they couldn't rely anymore on a vertical scale single point of failure, and they wanted to move to a more scaling out architecture. And this day is the day that Netflix decided to move to this microservice architecture, and currently Netflix is one of the major contributors to this environment. So this is my vision for a microservice oriented architecture for synchronization and sharing, where the logical components live on its own in different servers, physical servers or virtualized machines. And every component has its own database, let's call it like that. So you have the data management component, it will talk to the storage, the sharing to the sharing implementation backend, authentication to the authentication backend, and there is no really cross-pass in the core services. At the end, if you want to add like synchronization or sharing, you just need to put another services that rely on the core services of your infrastructure. In this case, for example, you can plug the synchronization service that talks to the different services like data, sharing, or the authentication. So these are some of the technical requirements to get the microservice architecture. You really need to be stateless as possible to scaling out without maintaining any state between the user and the server. You need service discovery and registration, health checks, and distributed tracing. So stateless, the first request hit node 8 in a cluster, second request hit node 3, and do you really need to maintain any states? So it's going to be deterministic. It doesn't maintain any state between user and the server. You also need service discovery. So if service A want to communicate with service B, you cannot really, in a microservice architecture, specify statically that service A will talk specifically to the server, because services are going up and down depending on the growing needs. So you need a registry. So every time you launch a node, you will register in the component that we call the registry. So you have a list of different nodes with different responsibilities. So anytime a service wants to communicate with another service, this service A will ask the server registry where is the socket for service B, and then it will start the communication. But what happens now if some nodes dies? So you need health checks. Every now and then, all the nodes in the cluster will communicate to the server registry, pinging this registry to say I am alive. And if I die, then the registry just removes this node from the registry. So there is no more that request from service A to service B. And last is the distributed tracing. From operational perspective, you really need to know, since the user started the request can go through a lot of different microservices. So you really want to know through all of the services that the request has passed through. So these are some pros and cons of this architecture. The benefits are that it's really independent. You have really independent and loosely coupled services. It's very easy to add new features. You just add a new service with another feature. You have a better resource allocation. You can fit hardware like a machine that has a lot of CPUs with a really CPU-intensive applications. And also, if you have a really application that really requires a lot of memory, you can use a specific hardware node for that. You have a small code base, so it's really cheap to adopt new technologies, as rewriting this little piece of code is easily and shouldn't take too many weeks. So it's really easy to change technology and let the developer the freedom to choose the technologies they want. It really goes hand by hand with modern technologies like Docker and Kubernetes to deploy this type of services. And the feature I really like it is with microservices, you really ensure a lot better system stability. As you can really replace one technology by another, you are not looking to a specific technology or to a vendor. So in the future, you can really switch without spending too many resources on it. So in order to test these architectures, I built a little system, ClawIO, that is my Swiss Army knife for my ideas. I presented last year at CS3 as a benchmarking tool for testing the on-clock synchronization performance. It's a configurable modular server daemon that can act as can be configured for working in a monolithic architecture on a microservice architecture-oriented mode. There is some prototype web application and CLI. It's written in Go, no dependencies, and it's very easy to use. So this is ClawIO exposes like 4 APIs. The 3 APIs, core APIs, are based on RPC oriented, follows the Dropbox API to version style, and they are very simple and very lightweight. And the last, for synchronization, I decided to use the OnCloud WebDAV synchronization protocol. So I implemented the protocol in a little microservices. And now I will let you know how is the testbed. So this is the testbed for a monolithic mode. I have a tool here, the ClawIO WebDAV bench, that connects to a physical bot that runs the monolith with a MySQL database and local storage over a 1 GB per second link, and run a profile test against the monolith. For the microservice architecture-oriented mode, I have the ClawIO OnCloud WebDAV process that the only thing it does is just translate the WebDAV sync part of OnCloud to our internal APIs, HTTP, over 1 GB per second link, and connect to different clusters, data nodes cluster, metadata node cluster, authentication nodes. So I decided to see what are the costs of using a microservice-oriented architecture against the monolithic one. So I ran a profile. I launched 5,000 requests with a different number of concurrent clients. The payload of the profile was really little, because I wanted to see the network influence, not the CPU performance. So with the monolithic approach, these are the requests per second in Earth here. So 114, 685, etc. And this is with the monolith. So what happens now if we enable and we move from monolithic to microservice architecture with one metadata node? So we get worse results because we have added the network latency. But what happens when we start adding more metadata nodes for handling the profiling operation? Well, if we just add 2 metadata nodes, we see that for serial operations, we still have the network problem because the operations are serialized. So we are really the same problem as with just one node. But we can see that as more concurrency we have, the results are getting better. And I did the last test with 3 metadata nodes, and you see that there's still a lot of improvement. And I ended my test here because I was running out of file descriptors in my local test machine. So the idea is in the future to add more tests with a really big cluster. So as a conclusion, I think that microservices for sync and share could be really useful if you are using a distributed object store system for large deployments. So you can really get a lot of benefits parallelizing operations through data nodes and metadata nodes. Also, it will allow you to use efficiently your resources. You can adjust hardware to software. And also, it really plays well in containerized deployments. This is an example of, for example, launching 30 OnCloud data nodes in a Sware environment. And that's it. Thank you.
Thank you very much. And again, well on time. Any questions for Hugo? What service bus are you using? Did you just pick one or just write one? Or?
For what, sorry?
The service bus in between the microkernel tidbits. How do they talk to each other?
With HTTP.
Plain HTTP?
Yeah.
No underlying definition or standardization that you just happen to pick?
No, I just created my own APIs, follow them. Yeah.
Right.
Yeah.
It is a plaything, so that's all cool.
Yeah.
But I mean, if you were to, I'm guessing you have no plans to move this, actually push this thing into production.
No. This was for just to testing if the microservice architecture against the monolithic, it was some benefits or not.
Understood. Yeah. No, it's potentially you could then distribute the microservices across different CPUs or even across different
servers. Yeah.
Servers.
Yeah.
Have you done that?
No. Just with these two boxes.
Just, you know, it's enthusiasm. I'm not berating. It's just like, hey, the things you could do. But anybody else? Yes? Towards the back?
Maybe I didn't get this correctly, but would it be possible then to start those microservices on request, if the number of requests is set? Yes. That you can just add them using the Kubernetes cluster? Yeah, exactly. The idea is that usually you have like a monitor, so you start like basically every microservice generates some metrics to like handle like Prometheus or I don't know, Grafana or whatever. So you have a monitor that can really every now and then checks what is the load and can start or shut down different services, so you can efficiently handle the loads of the user without spending too much resources on it.
Any further questions? Yes, towards the back, yes.
Sorry? No, just the network. In these tests? No, they were on physical boxes. The latency was like 0.5 milliseconds. It was a 1 gigabyte per second link into the servers between physical boxes. It was just the network latency between the services.
Yeah, so your underlying design assumption is that all of this is going to run in the same data center.
I could put it in different data centers, but I didn't have
the underlying for
yeah.
them, of course, but you don't know what it's going to do. So I think the question is, have you tested this to see whether it breaks at particular latencies, whether there's service degradation or that sort of stuff?
That would
Which
be
of course
something really
it's probably the same sort of enthusiasm that I'm sort of like, hey man, how does it work? But of course, I mean, but
this is really
it's pretty easy to actually add latency in the kernel, but that's for another. Further questions? No, because you're all, of course, keen